Why might the three-dimensional world be a holographic projection? Have you ever thought that if a two-dimensional photograph can fully record the information of a three-dimensional object, then with just a beam of laser, we could reconstruct the entire three-dimensional image? Even more astonishing is that every viewing angle and every fragment contains continuously varying information. This idea of compressing a three-dimensional object onto a two-dimensional surface and embedding the information of the whole into its parts is the famous holographic principle. Imagine that a beam of light actually contains both amplitude and phase information, while traditional exposure is only related to the square of the amplitude. If we use a beam splitter to divide the laser into two coherent beams, we can form concentric bright and dark interference fringes on a screen. Depending on the distance, the density of these fringes changes. In other words, you simultaneously record the amplitude and phase information of a point. Finally, by superimposing multiple points, we obtain a two-dimensional projection that contains all the three-dimensional information. In this regard, Nobel laureate Gerard de Hooft pointed out that if we do not need to measure the interior of an object at all, yet can reconstruct all the information at every point, then the three-dimensional volume may be only an emergent illusion, and the real physical processes occur on some two-dimensional surface. For example, the information content of a black hole is proportional only to the area of its event horizon, not to its three-dimensional volume. The remaining question is, if every region of a hologram contains the complete information of the whole, then it possesses statistical self-similarity, just like a branching tree. When you zoom in, it still exhibits the same patterns. Does this mean that there is a deep connection between the holographic principle and fractal structures?